So I have to say that explanation again. So next week, Roy's going to come teach you guys recursion. A big part of recursion is fractals, so we're going to do a little thing over fractals. So this is a very gentle introduction. So if you look at a sphere under a microscope, eventually you reach a point where it's flat. Everything here, you do that. No matter how curved it is, if you look at it close enough, it'll be a flat line. The true nature of a sphere, in a nutshell, is only appreciable by a certain distance. So you get far enough away, you see it as a sphere. If you get too close, it just looks like a line. But fractals essentially give us the ability to see an infinite level of detail. It's very useful in programming games because you can set your trees to be fractals, and they'll all be different. But the closer you get, you see more and more detail. So some fractals exhibit a property called self-similarity. Zooming in on a part reveals the same complexity of the whole shape. Inception, very Inception-like. And you can create it by doing it an infinite number of times. So this is the Koch snowflake, which a very simple type of fractal created in steps, adding more. First you start with a triangle, and then you add a triangle, 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 then you add a triangle. And you can do this with recursion in Python or any programming language. So it only truly appears after an infinite amount of iterations, and it gets an infinite amount of detail and such. So there's a specific reason why fractals are called this, but in order to understand it, let's talk about dimension. So you guys know what a one-dimensional thing is? What is a one-dimensional thing? It's the line. So two-dimensional is a plane, three-dimensional is a volume. So what makes it something one-dimensional? The idea behind the concept of dimension lies in the intuition that any point on a one-dimensional object requires only a single number of uniquely addressed things. So as you see the three little pictures below, that part is just one-dimensional, and then whenever you turn, so it's actually x would be one-dimensional, x and y would be two-dimensional, x, y, and z is three-dimensional. So in a two-dimensional shape, two coordinates are actually required to address each point, whether they express in the Cartesian, up, down, middle, or polar opposite, up, right. There's no escape for that. You have to have two numbers to see where a point lies in a two-dimensional field, right? Everyone remember this from geometry, pre-algebra, all that good stuff? So what is a ball, like, you remember the graphs, you do the little plus sign, you have the field. What is that? How many dimensions is that? Two, yeah. Up and down, left and right, yeah. So if you go back to the Koch snowflake presented in the previous section, you think that it would act like a one-dimensional entity, but a single number, you can't really give a point on that. So it's not a two-dimensional entity, since you can't really do that either, since as you add fractals, it becomes a three-dimensional. So, but it's sort of in between 1 and 2. It's not a three-dimensional. And I'm not interested in teaching you guys what that is, but it's trapped between 1 and 2, has a dimension that's not a whole number, but a proper fraction, which is why it's a fractal dimension. So, measuring complexity, one-dimensional, two-dimensional, three-dimensional. There are different ways to measure the fractal dimension depending on how the fractals are built. In the case of the Koch snowflake, the Hausdorff dimension is used, designed to capture how much length, the surface, or volume of a fractal changes with each iteration, which you will see that on Tuesday, but he won't explain it. But you'll kind of understand he's using in his calculations that he puts into Python, it's using the Hausdorff dimensions. So that's kind of a zoom in of the Koch snowflake.
So it only adds the triangles to the edges?
Sort of. kind of. Essentially, this line still exists here, here, like here, 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 here. Essentially, that line is being added upon. So, in conclusion, this is a gentle explanation of fractals, but let's talk a little bit more. Let's go a little bit more. Let's go to the Mandelbrot set.
That's a conclusion. I mean,
Now we got one more. So,
it's imagine being stone with something like that.
yeah. So that's just a fractal. This is a 3D. This is essentially a 3D fractal.
Did you forget to also take our LSD before class?
No. You know what? You don't want to end up like Ozzy. So essentially, whenever you're calculating a fractal, you can use this sort of set. A function of function subset c of x is equal to x squared plus c. So in order for this fractal to appear, both x and c must be complex numbers. And you can look up complex numbers later. In the context of a 2D rotation. So the complexity hidden of f subset c comes to light. I think that's how you say that, f subset c. Comes to light when you keep repeating the iteration over and over and over. So z of 0 equals 0, z of 1 equals function subset c of z of 0, so on and so forth. And you get something like this. So why is that interesting? Well, as you zoom in, each iteration of itself is an iteration of itself. So this right here is an iteration of this. Oh, this is an iteration of this, which is an iteration of this, so on and so forth. So it just keeps going infinitely. Yeah, this is the of itself. It is built within itself. So
That's just wild. I mean, like.
And this was done with this calculation right here. So very simple, but you have to do. See, let's what are some of the pages not found?
Oops.
Well, we can just type in.
Who's Alan's who?
He is a mathematician at somewhere, Yale maybe. And he didn't talk about himself, so maybe he's not at Yale. He'd probably talk about himself. Yeah, so like I squared equals -1, that would be a complex number. You can't really use that in this, but E is a complex number. You guys remember E, the business? There's a bunch of them.
Do this with negatives?
Because I mean, it's going to go to the left rather than to the right, depending on what it is. So, ugh, I remember this crap.
Horrible.
Yeah. I won't have you guys like you're not gonna have to know why this is, but just this is some of the stuff that he's gonna use. Granted, he doesn't use them because of. I mean, he wants to get if you want to get a certain output, you'll use a certain complex number, and that'll give you something. So. He isn't going to say, use this because of this. He's going to say, if you use this, it does this. So as you color it, as you can see, depending on how you color it, you get a bunch of different iterations of itself with different colors. And so this is all just done with fractal geometry. So.
They did a lot of this like Doctor Strange.
Well, a lot of games will use fractals in their environments.
Yeah, like rocks will be fractals.
Yeah.
Trees, grass.
Trees, especially grass, leaves. So.
Every individual snowflake that'd be like.
Yeah.
That'd be pretty cool.
It's really easy. Yeah, if you're going to make a snowflake, if you want to make snowflakes fall, you can use small little recursive drawing to make these snowflakes all look different. So no, I mean, granted that would be a little overkill because most people aren't going to analyze each individual snowflake, but you could do that.
It'd be like unneeded.
But you can do it for stuff like trees. If you want to make randomly generated trees to look a little bit different from each other, or you can just make 10 trees and then just put them in your forest. Most people won't notice the difference.
Trees.
So this is the Mandel bulb. There's an example of that. All done with fractals.
It's like a bacteria or something.
Some sort of plant bulb. So that's done with this right here. So you guys remember cosine and all that good stuff? Sine, cosine.
Oh, that's Cal 3. We're about to
This is just trigonometry.
Well, yeah, but Cal 3 is from trigonometry. Yeah, advanced.
So
It is?
Yeah.
Ew. I don't like that.
So the Mandel-bulb sequence is this right here. V of 0 equals 0, 0, 0. V1 is G subset, well, G of C of G, G of C, V of 0, so on and so forth. So there was one that showed, let's do, so here's a tree. Here's an example. He's going to show you how to draw this tree. Because essentially, this is a branch. This is the trunk, branch, and each individual tip of this right here are all just those same Y's. So here's I forget what they call it, something triangle. Sarkisian, I forget what it's called, but Sierpinski triangle. And the interesting thing about this is, as you draw it, if this were color reversed, little circles pop up, just built in. So it's really cool. I think he's going to show you this Sierpinski triangle, and then here's if you use squares, the square tree. Essentially, this is a square, but it kind of looks like it has curves, despite it just simply being. Here's the one with circles. So this is all recursive drawing. That's a pretty cool one. So, and as you change the formula, then you can get different looking trees. This one looks a little more like a actual tree. That one was drawn.
I was about to say, that's really good.
Yeah, here's a fractal one.
That's really good.
Yeah, there's not, if you have a really crappy two-dimensional game, you could use something like that. But if you're wanting to make something look a little more realistic, you do something like that, something in the distance. So like I said, you can do a lot of pretty cool stuff. It's like this one, you have a star built in there. Not due to them drawing it, but that's just how it turns out. This one this one looks like this one has the Fibonacci sequence built into it as well. That might be the silver rule. So now whenever he's talking about this stuff, you guys will be completely clueless. And we're also gonna, and then I don't know if it's gonna be Thursday or the Tuesday following that, which I think is Thanksgiving, isn't it? So it might be Thursday. Jairus is gonna come in and he's gonna teach you some real life Python stuff. They made a program that essentially would create false students and then vote for something. So like there was like a costume contest, and they just wanted to see if they could rig it, and they did. Granted, someone spotted some of the names and noticed that they weren't real, so they canceled all the votes for it. But they essentially made a program that could falsely vote for something. So if you guys want to rig an election, Jairus is going to teach you how to do that. I'm not sure if that's exactly what they're doing. They might teach you something else,
Hey.
but
Let's have a revenge 2020. Okay.
so I had a quick question for you guys.